Thank you. Thank you very much for the introduction. So my name is Shanghao Shi, and I'm currently a PhD candidate at Virginia Tech. So today I'm going to talk about our recent work about the model inversion attack against the federated learning system. So for the federated learning, I mean, everyone may be pretty much familiar with it. So federated learning was considered to be a privacy-preserving mechanism. It allows the clients to collaboratively train a model without sharing any local data. So within the federated learning framework, only the gradients or the model updates are shared between the server and the clients. However, there are some potential privacy leakage possibilities. So this is because the global model and the individual model updates or the aggregated model updates are actually exposed to the attacker. The attacker is usually the parameter server, and the question is, can the attacker actually retrieve any meaningful information from this exposed information? And unfortunately, the answer is yes. There have already been some state-of-the-art privacy attacks, such as the membership inference and the model inversion attacks, or we can call it the data reconstruction attack. So for this work, we are focusing on the second one. We are actually a model inversion attack. So this model inversion attack is launched by the parameter server. So it aims to reverse the individual or aggregated model update back to the local training samples. For the attacker's knowledge, we assume they know the global model and individual model updates, and their goal is to reconstruct the local data. So existing works, there has already been some optimization-based attacks. For example, the gradient inversion works. So they actually formulate this pretty complex inversion task as an optimization problem. And the fundamental idea for this line of the attack is to gradually optimize dummy samples towards the original ones through doing some optimization stuffs. However, there is some key limitations for this line of the work. The first one is that they suffer from pretty much poor scalability, and they have very large overhead. For example, you need to have hundreds of seconds just to use the optimization tool to reconstruct a few images. And the second limitation is that there has already been some kind of cryptographic defense mechanism called secure aggregation to prevent them. So the secure aggregation mechanism is actually a multi-party computation protocol aiming to protect, or we can say enhance, the privacy of the federated learning system. They are very complex cryptographic protocols, but their fundamental idea is to add a cryptographic mask to the original local model update so that the server cannot distinguish them from even a random number. But at the same time, they ensures that the summation of the mask outputs, they equals to the original one. So in this way, you can keep going on with your, the training process on the server side. And, as the attack and defense is actually an arm race, so there have already been some works that compromising the secure aggregation protocols. So there's one interesting work called the linear leakage. It is actually a very powerful mathematical tool that can reverse the aggregated model updates back to the inputs. So here is the formal definition of it, but let me just provide some key concepts for this attack. So the key concepts for the first one is called two subsequent linear layers. So in order to launch this attack, you must have two linear layers. So this is why it's called linear leakage. And for the second important thing is that they can deal with the batch inputs. That means even if your results are aggregated, it's not secure anymore. And here is a figure showing the fundamental idea for this attack. So basically, each sample is actually reconstructed by one neuron in this architecture. And naturally, there comes one line of the attack called the model crafting attack. So because you have such a magic attack module, you can just insert these modules in front of your original model architecture. Because these modules are mathematically crafted to inverse your model updates back to the training samples, you can just put it in the front. However, the key limitation for this model crafting attacks is that you change the model architecture, and this is pretty much obvious. And the and a defender can easily tell that the model has been compromised. So for our work, we are actually adopting a weaker attack model. We do assume the attacker to be able to change the model parameters, but we don't assume them to be able to change the architecture. So also we follow the same assumption as the existing works. We assume the attacker to possess a small auxiliary data set, and the goal of the attackers is again to efficiently and effectively reconstruct the training samples from the aggregated model updates even after the secure aggregation. So this seems to be quite a complex task. So how can we achieve this? So let me provide some intuition for this. So as long as you add an additional module, it's too obvious. So can you actually leverage any existing layers within the model? And the answer, of course, is yes. So we are going to leverage the linear layers in the latent space to help us. So almost all classifiers have this architecture, and in the latent space you have enough information, and in the latent space also you have lower dimensions that help you reduce the overhead. And again, even if you just use the linear layers or the linear leakage module to help you do the inversion in the latent space, you can just get some intermediate result. That means you can just reconstruct the representations within the latent space. There are still a lot of the nonlinear layers in between. I mean, between the input and the latent space. How would you handle this? So actually, we propose an innovative two-step reconstruction to handle this. So for the first step, you can use the linear leakage to help you reconstruct the intermediate representations, and in the second step, you can further use a generative decoder to help you overcome all the nonlinear layers. And basically, it works like this. You start from the aggregated model update, you use a linear leakage to gather representations, and then use a decoder to help you generate the input samples. And this is like the autoencoder stuff. So I'd just like to have a quick revisit of it. So it consists of an encoder and a decoder, and it can help you deal with batch inputs and reconstruct them at the the output side. Okay, here is the general attack flow of our mechanism. So our mechanism is actually a two-phase attack, including the preparation and the actual reconstruction phase. So if you remember, we have talked about the two-step reconstruction. So that is referring to only the second phase, the input reconstruction phase. For the first phase, it is conducted purely on the server side. The server actually locally crafts the adversarial global model, which consists of two important components, including an encoder and two linear layers. And these adversarial global models are then disseminated to the clients. The clients who will not aware of this, they will keep going on with their local training process and send back the the aggregated model updates, because we assume the secure aggregation protocol is there. And after that, the server again, because they are actually the attackers, they will take the aggregated model updates as the input and conduct the two-step reconstruction we have introduced before. The first you reconstruct the intermediate latent space representations, and the second you use you feed these representations to the decoder to help you generate input samples. So there are we actually have a pretty much rigorous mathematical proof and a definition for this reconstruction process. So I will just introduce the fundamental idea for this work. And if you are interested in the mathematical details, please check the paper. So for the implementation, we actually conducted our attack on up to 6 data sets, and we conducted our attack over different settings, for example, different number of clients and a different number of local training rounds, and we use the commonly used metrics to evaluate the reconstruction performance. So I provide one batch of reconstruction sample here. So it is actually 64 images from the Scalable A dataset. I actually plotted the original images on the left, and I also plotted the the reconstructed ones on the right. You can see that the reconstruction performance is pretty much good, and 61 out of 64 images were successfully reconstructed. So the key difference between our work and like the previous optimization-based attack is that our work can deal with the batched inputs and do the reconstruction for a whole batch of samples simultaneously. And here are some numerical results for the reconstruction performance. So many statistics here, but I will just provide 2 key points. So for the first key point is our attack can deal with, deal with the batch impulse. The batch size here is referring to the reconstruction batch size. This means how many samples you are going to reconstruct simultaneously. And the second key point is for the attack time. You can see that our attack can be accomplished very short time, even within 1 second. So this is very interesting. And we also evaluated our mechanism against the different attack factors, such as the number of clients. We changed the number of clients, and we find that the attack performance is not affected. We also check our performance against the data deficiency settings. That means we reduce the number of samples available to the auxiliary data set, and again, our attack performance is not significantly affected. And also the data scale, the interclass and intraclass data scale between the auxiliary data and target data. So the interesting point here is that our attack actually overcome the intraclass data scale. Well, I think that's intuitive, but we do face difficulty for dealing with the interclass data scale. So it's like if you only have the dog samples in your auxiliary data set as an attacker, you may have some difficulty for you to reconstruct the images of the cat samples. And another thing I want to mention here is we also evaluated our attack's performance over the differential privacy mechanism, because when we talk about privacy, it's naturally for people to think about the differential privacy mechanism, but unfortunately, according to our results, we find that differential privacy is not that effective against our attack. So in summary, we actually propose a novel model immersion or data reconstruction attack that challenges the privacy preserving mechanism of the federated learning systems. Our attack is very efficient and very accurate. And also we show that the existing privacy preserving mechanisms, such as the secure aggregation and the differential privacy, are ineffective. So this work, we actually have passed the artifact evaluation process. So if you are interested with the implementation, you can check the paper and also the code. So thank you very much, and I'm happy to answer any question.
Thank you very much. Hello. Okay, any questions? Your talk was so fantastic.
Thank you.
They understood everything.
Oh,
okay.
That's great.
So, but you said I think here was written something. We just discussed that you already have some job offers, right? No.
I do have some
interviews, perfect.
But I'm not sure.
So, thank you very much for your talk, and I hope that everything will go good.
You.
Have a nice life, and goodbye.